Now this is our next video where we will learn about principle of calorimetry. This is that basic method depending on which a calorimeter or any other method in mathematics you can measure the amount of heat exchange. That is the easiest method to do so. Now how does this method works? Basically, when you are mixing two things, that is when some heat exchange can take place. And when will it take place? There will be conditions that you have a first object at temperature T1, second object at temperature T2. Okay, now the heat transfer will take place. The heat transfer only take place if T1 is greater than T2 or T2 greater than T1. If they are equal, no heat exchange will take place. But if they are not equal, that is like first object T1 is greater than T2, then heat will come out of the first object and will move to that second object. Now the question appears, how long does that happen? That is, how long the heat transfer will take place? The answer is easy. Until they reach an equilibrium. Equilibrium here refers to what? Means at an equal temperature. Clear? I consider that I had two objects T1 and T2 where T1 is greater than T2. So from the first object heat will come out and it will move to the second object until they reach the equal temperature, which I will call T. Here. Now you can see T1 is greater than T2, so T1 will lose heat, so temperature will decrease from T1 and it will move to temperature T. And as second object is gaining the heat, the temperature will rise from T2. The temperature will rise from T2 and it will rise until temperature becomes T. Until temperature becomes T. Now see, we know how much heat is exchanged when temperature exchange happens. The formula is very simple. Q equals to mc delta T. I hope all of you remember this formula from the lecture 2. So Q equals to mc delta T, where m is mass, c is specific heat and delta T is change in temperature. Now the first object, how much temperature change happens? T1 minus T. It was at temperature T1 which was higher, it decreased to temperature T, so T1 minus T. Second object is gaining heat. Second object is basically gaining heat, so its temperature was at T2, it will now rise to temperature T. The second object temperature changes, T which is higher after it gained heat, minus T2 from where it started. So this is the change in temperature. Now the question appears, how much heat the first object lose? I consider the mass is M1, specific heat C1 of the first object, and we got temperature change, that is delta T equals to T1 minus T. So the first object temperature changes T1 minus T. So what is the heat gaining formula? In first object it is losing heat. The formula of losing heat, Q1 equals to MC delta T, same formula, equals to mass here M is M1, specific heat here C1, and delta T is T1 minus T. So this is the loss of heat. Now the next part, how much heat the second object gained? The heat gained by the second object I consider the mass to be M2, specific heat C2, and change in temperature we measured T minus T2. So heat gained is very easy. Q2 equals to MC delta T, that is mass here M is M2, specific heat C2, and delta T is T minus T2. So heat gained by the second object Q2 is M2 C2 T minus T2. Clear? Now say we got two things. First object loses some amount of heat. First object loses heat as its temperature was higher. The amount is Q1 equals to M1 C1 T1 minus T, and the second object gains heat. The second object gains that heat, and that amount is M2 C2 T minus T2. So it is very much questionable that the amount of heat lost by the first object is the amount of heat gained by the second object. Clear? Because the first object was hot and the second object was cool. You remember the first object temperature T1 was greater than the second temperature T2. So the heat loosed by the hotter body is equals to the heat gained by the colder body. What did we learn? That heat lost by hotter body is equals to heat gained by the colder body. We learned that heat lost by hotter body is the heat gained by colder body. They are equal. This thing is known as principle of calorimetry. This thing is known as principle of calorimetry. So in our formula, heat lost by first object is this, and the heat gained by the second object is this. Principle of calorimetry says that heat lost by the hotter body is the heat gained by the colder body. So this Q1, which is heat lost, and Q2, which is heat gained, are equal according to the principle of calorimetry. So Q1 is equals to Q2. Q1 is equals to Q2. What was Q1? M1 C1 T1 minus T. And what is Q2? M2 C2 T minus T2. And this is how we get our formula. This is how we get our formula. This thing is the principle or the law of the calorimetry in mathematical form, where T1 is the temperature of hotter body, T2 is the temperature of colder body, T is the equilibrium temperature, the temperature where the heat transfer stops. Clear? What is C1? C1 is the specific heat of hotter body. C2 is the specific heat of colder body. And M1 and M2 are the masses of cold object. Clear? This formula will be basically used to do the most of the numericals in this chapter of exercise 11a. So take a brief look at this formula. Clear, I think? this formula is the most important out of all. In the next video, we will learn how to solve the numericals. In the book portions, you will find out that some examples are asked about what are the advantages of having higher specific heat capacity, advantages of having lower specific heat capacity. I think those examples can be learned by you. They are very easy. Just like why water is used for in any kind of hot water bag for giving any kind of heating. Why do we use water? Because water has a higher heat capacity, so it will contain the heat for a longer amount of time. It will also absorb a good amount of it. So what will happen? It will help us to give heat for a longer amount of time. That is the use of water. And just like the lower heat capacity, we know any object of lower heat capacity will absorb less amount of heat. So they are basically useful for making things like calorimeter. You know why copper was used for its lower heat capacity. So these things can be understood by you. They are very easy examples discussed very well in the book. So, and some examples are also discussed of high and low capacity cases. I'll leave these things for you. In the next video, we will learn how to solve some numericals from the book. In the last video, we have solved up to 7 or 8 number of numericals. Let's see in the next video. Thank you.